Well, then, thanks to the half of you who came. So this is the last lecture, of course. So let me start from where we stopped this morning. So I ended up writing the expression for the likelihood, which was this expression here. So remember, the likelihood is the probability of having data, the signal S, given the parameters. So we managed to show that thanks to Bayes' theorem and to the assumption that the noise be Gaussian, the likelihood takes this form. So this is, and then what we did was to expand the likelihood in near its maximum. So we looked for a maximum which satisfies this condition, and this equation gives you the parameters that best fit the data. And then what we did was to expand in a Taylor series at quadratic order around this maximum. And under this quadratic approximation, the log of the likelihood is simply given by this quadratic form, gamma ij, and this delta theta are the deviations of the parameters away from the best estimator. And this gamma function is what we call the Fisher information matrix. And this is, in fact, the inverse of the covariance matrix. Why is it called covariance matrix? Well, if this was just one dimension, if we just had one parameter, this expression, exponential of -1/2 gamma delta theta squared, would be simply the Gaussian probability distribution. So this gamma would be 1 over sigma squared. When you have more than one parameter, the Gaussian, multidimensional Gaussian distribution is, or PDF, is described by an expression like this. And this, in fact, I wouldn't need to write on the blackboard now, but that's fine. So essentially, this matrix gamma, or actually the inverse of it, which is what we call the covariance matrix, encodes on the diagonal the errors of the parameters, or actually the variances of the parameters. And on the off-diagonal terms, it encodes the correlations between the parameters. So if you have your favorite waveform model, you just need to take derivatives between, with respect to the parameters, take internal products, construct the Fisher information matrix. You can invert it, and then on the diagonal, you'll have the errors of the parameters and the correlations between the parameters in the off-diagonal terms. In fact, this is what I was writing here. The errors on the parameters are given by the diagonal terms of the inverse of the Fisher, which is the covariance matrix. And there are more, so this is in principle is a quadratic approximation that is only valid in the high SNR limit and very close to the best estimator. In principle, however, if you have some data S and some model H of T, where T are here the parameters, you could use this very expression and plot it. So suppose I have a model which depends on some parameters. I have the data, so I have everything I need to plot this likelihood as function of the parameters on the whole parameter space. Because I know H, once I give the parameters, I know how to compute H. S are the data which I have. There will be a time series for LIGO or LISA or any other detector. So in principle, I could plot the likelihood, the whole likelihood. This is, however, this works if you have a few parameters. Because gravitational wave observations, or actually gravitational wave models, typically have lots of parameters. In particular, this H, this strain, in the fully general case, has 15 parameters because it encodes information about the masses of the binary system, the spins, the initial phase, the merger time of the system, the sky position, the orientation of the binary with respect to us. There will be plenty of parameters. In particular, for each gravitational wave source, there will be 15. So this is a function in at least 15 dimensions. So it's very hard to plot it. And in fact, to explore, and this is even worse in cases in which you have several gravitational wave sources superimposed to one another, which is typically the case for LISA, as I will say maybe in the end, if I get some time. So in practice, this likelihood function is a multidimensional function, and therefore to just plot it is not a viable option. What you need to explore this likelihood function are more advanced techniques, which are called Markov chain Monte Carlo techniques, which are exactly used to essentially to understand the structure of the likelihood. So this is far beyond the scope of this lecture, but keep in mind that what you do in practice is not just to plot the likelihood or to use a Fisher matrix approximation, but you use full-fledged Markov chain Monte Carlo techniques. So this was what I wanted to say this morning, and I didn't have time, so let me start, let me change gear and go to what I want to say in this lecture. So before I go further, I wanted to summarize the difference between gravitational wave astronomy and electromagnetic astronomy. So today I'll be talking about gravitational wave astronomy. So I want to emphasize the difference with respect to traditional astronomy. So one of the differences between gravitational waves and photons is that gravitational waves or gravitons interact very weakly with matter. So they're essentially all of the universe is transparent to gravitational waves, unlike what happens, of course, for photons, which interact strongly with the rest of the standard model. The other difference is that, as I emphasized several times, the gravitational wave signal amplitude, h, decays as 1 over the distance, as 1 over r, or actually as 1 over the luminosity distance, as I explained this morning. So whereas electromagnetic fluxes decay as 1 over r squared, and therefore they decay faster. So gravitational waves allow you to go to much higher redshift than most electromagnetic observations, with the exception of radio observations, which are sensitive to the electric field, which also decays as 1 over r. So the other difference between gravitation and electromagnetic astronomy is that the gravitational wavelength, as I was explaining yesterday in response, I think, to a question, is typically for LIGO of hundreds of kilometers. So gravitational wavelengths are very large. They're much larger. Well, in fact, they are larger or comparable to the source size. This is what I was explaining yesterday. If you take the quadruple formula, the gravitational wavelength is given by the separation of a binary system divided by the characteristic velocity of the binary system. So gravitational wavelengths are large compared to what happens for photons, whose gravitational wavelengths are typically microscopic. And why is that? Because unlike photons, which are typically emitted by transitions in atoms or in molecules, gravitational waves are produced by the bulk motion of very large systems, such as black holes or neutron stars. So this is an important difference, because it means that the gravitational waves do not have much angular resolution, simply because the wavelength is very large. Unlike photons, or at least optical photons, or X-ray or gamma rays, which can be used for imaging because they have very small wavelength. On the other hand, we have an advantage with gravitational waves over electromagnetic astronomy, is that gravitational wave detectors are sensitive to sources essentially on the whole sky, with some blind spots, some regions, some directions in which they are less sensitive, but nevertheless they have an antenna pattern which covers a good portion of the sky, whereas as you know, with traditional telescopes, it's very hard to have full sky surveys. So in this sense, the two are different and in a sense complementary. So I mentioned that the gravitational waves alone have very little sky localization power. This is an example, probably you have seen it already. This is the first gravitational wave detection from the merger of two 30 plus 35 solar mass black holes, 150914, the first ever direct gravitational wave detection, and it could be localized. It was detected only by the two LIGOs, and it was localized in this banana-shaped sky region. So it's nothing compared to what you would obtain with an electromagnetic observation. So it's a very large sky region. On the other hand, this is okay. So this is in fact another black hole binary. It was the first black hole binary that was seen at the same time by the two LIGOs and by Virgo. And as you can see, by the fact that you have 3 detectors, you can localize it much better in the sky. It's still several square degrees, but you can simply do triangulation. So the more detectors you have, the better the sky localization is. And sorry, I forgot to mention, of course, because these lights are a bit old, but if you have also clearly an electromagnetic counterpart, such as in the case of 2 neutron stars, in which you have a GRB, of course, you can pinpoint the source in the sky. But then again, you do it with electromagnetic astronomy and not with gravitational astronomy. So I mentioned that if you have a network of detectors, then you have a better sky localization. So these are, well, I'm not sure if I should go through this in detail. In the future, we'll have many more gravitational wave detectors than just LIGO and Virgo. We'll probably have Kagra in Japan in a couple of years. And down the road, we'll also have a gravitational wave detector in India, LIGO India. So they'll ship one of the LIGO detectors from the US to India to attain better sky localization. So this is, well, I don't want to go into the details, it's pointless. So the more, so H stands for Hanford, L for Livingstone, K for Kagra, and there, H and H are the 2 Hanford LIGO detectors. Because in fact, I'm talking about 2 LIGO detectors, but in fact there are 3. There are 2 LIGO sites, one in Livingstone, one in Hanford. And the Hanford site has actually 2 coplanar detectors, so it's actually 3 LIGO detectors. So H are LIGO, L is LIGO, K is Kagra, V is Virgo, etc. And that's, so the more detectors you have, the better the sky localization. Although, as you can see, it's still patchy. So the sky localization, this is for a simulation for a given source. The source could be anywhere in the blue regions. Similar sky localization problems are affect other gravitational wave detectors, such as pulsar timing arrays. So maybe I'll say a few words about pulsar timing arrays in the future. So this is, all these results are again obtained by sampling your likelihood. Yes? You get, if you have a network of detector, yes, you can get both polarization. I'm not, say again? No, each detector gets, I mean, each detector is sensitive to a combination of H plus and H cross. So if you want, this is what I was writing this morning. So the response of a detector is given by the pattern function for the cross mode times H cross plus the pattern function for the plus mode multiplied by the plus mode. So if you want to break with a single detector, you'll not be able to measure polarizations. You need at least 2 detectors. And then the more detectors you have, the better. Is this what you're asking? Well, if not, ask me again later. So why am I showing you these results now? Because this comes from this from Bayes' theorem. So when people get these sky localizations, then it comes really from sampling the likelihood, which is what we showed before. So all these exercises of parameter estimation require sampling that likelihood. So in a sense, there is nothing profound about gravitational wave astronomy. It's simply Bayes' theorem. It's, you need a model that comes from GR, and you need a good sampler, a Markov chain Monte Carlo sampler, and of course you need a detector to obtain the data. So what do I want to say now? Yeah, this is what I was saying before. Of course, if you have a counterpart, such as a GRB, you'll be able to localize, to pinpoint your source in the sky to very large accuracy, although, as you can see, it's still several square degrees. This was the sky localization of GW 170817, the first ever direct gravitational wave detection from a neutron star binary. It was it came at the same time as a short gamma ray burst, which was then interpreted as due to the binary. and this allowed us to localize, or them, I'm not in the collaboration, to localize the source in the sky. And then they observed the system for several, in fact, they're still observing the afterglow of that event to this day. Especially in radio, the emission can be very long-lived. And of course, once you pinpoint a source in the sky, you can measure its redshift electromagnetically. So in the case in particular of the neutron star event, they could measure the redshift of the source, and then the gravitational wave signal gives you the luminosity distance. So I insisted this morning that one of the parameters of the waveform is the luminosity distance. So that, again, by doing your Markov chain Monte Carlo, you can extract from the data. And then electromagnetic astronomy can give you the redshift. So if you have a DL and redshift, you can measure, at the very least, the Hubble constant. So these were the measurements for the Hubble constant that came from Planck and from other surveys. And this curve here was the PDF, the posterior PDF that comes from your Markov chain Monte Carlo and from the measurements of the redshift. So this is essentially the measurement of the Hubble constant by LIGO. And as you can see, it's sort of the maximum, the best estimator is sort of in between the Planck and this galaxy survey measurement. I think it's I'm not entirely sure what this, maybe it's supernova, I'm not sure. Anyway, so there is some controversy in cosmology as to what value the Hubble constant should take, because this chooses a local measurement of the Hubble constant, whereas Planck is a measurement of the Hubble constant based on very high redshift, because it's the CMB. And gravitational waves, if we have more measurements, could actually tell the difference. And this is, for cosmologists, that's an important point. Okay, so so this is in fact what I want to say this morning. So what I want to say in the next hour or so, because then we need to stop, is to try to say something more about the physics of gravitational wave emission. So we're all familiar with this image that you've probably seen several times. I didn't draw it on the blackboard, but I'm sure you've seen it before. So this is the gravitational waveform, the strain from a binary system of two black holes, which orbit one around the other. They lose energy through gravitational waves. We derived the energy loss in gravitational waves. And at some point, the two black holes come together, they merge, and then they give rise to this signal, this exponentially damped sinusoid, which we call sometimes ring down. So I want to go more, although qualitatively, more in detail about the physics of this waveform. So we saw already the in-spiral phase to some extent, because we derived the quadruple formula. So this is the chirping part of the signal, as we also call it. You remember Andrea and myself as well wrote equations for the rate of change of the frequency with time as obtained from the energy balance and from the quadruple formula. And if you remember, the frequency was increasing. And you see this exactly here in this. You see that the period of the oscillations decreases. So it resembles somehow the chirp of a bird, so it's called chirp. I don't have any sounds, but you can find on the web sounds corresponding to this waveform. So I will try to make sense of this, and in particular I will use things that hopefully you guys have seen at some point or another during your GR classes, namely the concept of innermost stable circular orbit, circular photon orbit, or light ring and event horizon. Who hasn't seen any one of these three things? Don't be shy. Well, I'll go through which need light ring you haven't seen. Okay, well, I'll have a slide explaining. So luckily, I will not need that until the very end. So for the moment, I will focus again on the chirping part of the waveform, for which I will need essentially the innermost stable circular orbit. So since all of you have seen this one way or another, let me be very quick about it. So the innermost stable circular orbit, or ISCO in short, is, as the name says, the circular orbit with the smallest possible radius that you can have around a schwarzschild or Kerr black hole. A Kerr black hole is a rotating black hole, for those of you who have never seen this. So essentially, what happens in Newton, if you have a point-like source in a point-like mass in Newtonian gravity, you can get as close as you want to it. You can get circular orbits that are arbitrarily close to that point mass. This is a feature of Newtonian gravity which is not conserved in general relativity. So if you have geodesics around a Schwarzschild black hole, because of the symmetries of the Schwarzschild metric, you can write down a conservation equation for the energy that looks like something like this. So you have R dot, which is essentially the kinetic energy of your particle orbiting in this black hole space-time, plus some potential energy, and this must be constant. So, and if you plot, so in particular, this effective potential, so in particular, you can move this effective potential to the right-hand side of this equation, and if so, you get an inequality, because you know that R dot squared is always positive, of course, so you get regions that are allowed, and radial regions that are allowed by this equation, and radial regions that are forbidden. So for instance, you can plot this potential VR, this effective potential, and you find that you can only have circular orbits, stable circular orbits, at radii larger than 6m. This is done in most textbooks. I don't have time. And the radius at which your circular orbit lies depends on the orbital angular momentum. So there is a term in this potential that depends on the orbital angular momentum, because there is a term in this potential that is essentially a centrifugal force term. So if you've never seen this, well, you can find it pretty much in any textbook, or you can derive it yourself. It's not very difficult, in fact, in Schwarzschild. But the key point is that at some point, at 6m, there are no circular orbits anymore. And so if you're, either you have unstable circular orbits, so the maxima of this effective potential correspond to unstable circular orbits, or you have just plunging trajectories. So at some point you reach, so if you're a particle moving around the Schwarzschild black hole, you will slowly spiral in this external, in the external space-time, until you, under the effect of gravitational wave emission, until you reach the ISCO, and therefore, and thereafter you plunge. You plunge onto, and you enter into the, essentially you fall into the event horizon. So this is one, so this was to make you understand intuitively why at some point the binary plunges, so that the same effect, in fact, applies to comparable mass binary systems. So it's not special to a particle in Schwarzschild, but it also applies to equal mass or comparable mass black hole binaries. So how about black hole spins? Black hole spins are also something that we can measure in gravitational waves that affect the signal, and I wanted to give you a qualitative, again, understanding of what black hole spins, what dynamical effect black hole spins have. So I mentioned in the, I think it was the first or the second lecture, the length steering effect, or also called frame dragging effect. So the angular momenta or spins in general relativity have a dynamical effect. So if you have a rotating black hole, you observer outside the rotating black hole will be forced to, well, it will be easier for you to co-rotate with a black hole than counter-rotate. So this is why we call it frame drag. You're dragged by the rotation of the black hole in that same direction. This doesn't mean necessarily that you can't counter-rotate. Well, depends how close you are to the black hole. So this effect, this tendency of an observer to co-rotate with a black hole is more and more important as you get closer to the black hole and as the spin of the black hole increases. So the spin has a dynamical effect, and in particular it also affects the position of this innermost stable circular orbit that I mentioned. So in particular, the position, the radius of the innermost stable circular orbit gets closer and closer to the event horizon of the black hole as the spin of the black hole increases. This is, again, a textbook calculation. This is the radius of the disk over m as function of a over m. A is the spin of the black hole, and the spin can't be larger than 1 because otherwise you will have a naked singularity. This is, if you've never seen the Kerr metric, this will not mean much to you, but I have to assume something to prepare these lectures. So this is the maximal spin is 1. The spin can't be larger than 1. So as the spin gets larger, circular orbits get closer and closer to the black hole. So if you want, the spin of the black hole circularizes or stabilizes the orbit. And this is not a purely academic effect. It is something that astronomers use every day to measure the spins of black holes using accretion disks. So this means that the radiative efficiency of accretion disks increases is a strongly varying function of the spin of the black hole. So the higher the spin of the black hole, the more efficiently accretion disks radiate. In particular, the efficiency can go from 5% for 0 spins up to several tenths of percent for high spins. This is why, so keep in mind that an efficiency of just 5% is a huge efficiency. So if you consider a nuclear reaction, the efficiency is much less than a few percent. So this is why we believe that quasars are black holes. Yes?
What do you mean exactly by efficiency?
Efficiency, this means how much energy. So if you're a gas element at infinity and you move in the disk until you fall into the black hole, due to viscosity, you will radiate away you will lose energy, some of your binding energy. Some energy will go away in heat, in viscosity, and that will be eventually emitted by the disk in the form of electromagnetic radiation. So how much rest mass of the gas, as seen from infinity, is radiated away in photons is this efficiency. So if you have 1 kilogram falling into the black hole at infinity, by the time you get, if you have a non-spinning black hole, by the time the mass falls into the black hole, it will be 0.95 kilograms. And this is in fact how astronomers measure black hole spins. So in fact, they use techniques which are called continuum fitting or iron K alpha lines, which are appropriate according to what mass the black hole has. So for instance, for stellar mass black holes, they use both techniques. So the continuum fitting means they use the continuum spectrum of the disk. Iron K alpha lines, they use certain lines of course, of iron fluorescent lines. And they're able to measure the spins, which for stellar mass black holes can take a variety of values, they're all over the place, whereas for supermassive black holes, so black holes which are 10 to the 5 or 10 to the 6 plus solar masses, the spins are typically very large and measured using this iron K alpha lines. So this is, again, so far I haven't talked about gravitational waves, but this is to give you an idea of what dynamical effect black hole spins can have. So in gravitational waves, the effect of black hole spins is exactly the same. So the larger the spins of the black holes, the more efficient gravitational wave emission is. So I mentioned before that when the spins are large, the innermost stable circular orbit moves inwards. Same applies to system of 2 comparable mass black holes. So this is an actual numerical simulation. It seems like a cartoon, but it is a numerical simulation. in full GR of the merger, the coalescence of two black holes. So here you have black holes which have spins pointing down on the minus 0.76 and orbital angular momentum pointing up. So the spins of the black holes is counter-aligned with the orbital angular momentum. So this is a situation in which essentially this is what you're here in this negative region. So this negative spins means counter-rotation. Sorry, but I didn't mention that. So this means that the spin is counter-aligned with the orbital angular momentum. So this is the case here. Spins are negative in a certain sense. And the binary plunges very early because the effective ISCO of the system lies at very large radii. Whereas in the case in which the spins are large and aligned with the orbital angular momentum, the plunge takes place very late because the ISCO of the system lies at very small radii. And this again has an effect on the gravitational wave emission efficiency, so how much energy is emitted or what fraction of the total mass of the system is released in gravitational waves. So clearly a system such as this, which performs just a few cycles and then plunges, doesn't have time to radiate much, just in the same way in which an accretion disk with whose inner edge is at very large radii doesn't have time to radiate much, whereas this system radiates much more, simply because the quadruple formula tells you that whenever you have a circular orbit, you emit gravitational waves. So the efficiency of gravitational wave emission is a strongly increasing function of the spin, and it goes from 3% up to 10%. So this is again a huge amount of energy. If you convert if you calculate the energy emitted by the LIGO events, those would be the most luminous sources in the universe, except that gravitons, as I said, interact very weakly with matter. So it's very difficult to detect them. We can't see them with our eyes, but it's a huge amount of energy compared to electromagnetic astronomy. Spins also cause modulations in the waveforms. So whenever you have vectors which are not aligned, you typically have modulations. So if the spins is not aligned with the orbital angular momentum, you have beatings in your gravitational wave signal. Forget about these gray lines and just look at the purple one, and you can see the amplitude of the gravitational wave signal experiences these beatings, and this is due to the precession. This is very similar to the spin orbit precession that you have in atomic physics, in fact. So far I've made so I'm trying to make you understand qualitatively how things behave. And I made the example of the Schwarzschild geodesics in Schwarzschild. I talked about ISCO in Schwarzschild and in Kerr. Of course, that is not appropriate for comparable mass systems of black holes. I can't think of the LIGO binaries as a particle orbiting around the other black hole. It's because they have comparable masses. So in practice, the way you do it is through a post-Newtonian expansion or through numerical simulations. But so I explained a little bit the post-Newtonian expansion the other day. I don't know how much has stuck if you've never seen that. But essentially, the post-Newtonian expansion is, as I was mentioning the other day, an expansion in 1 over c. So even though you can't treat a binary system in LIGO you can describe it by geodesics in Kerr or Schwarzschild, you can do something similar. If you can try to solve the Einstein equations order by order in 1 over c, and you can describe it with a Hamiltonian, just like the one. So we started deriving this Hamiltonian the other day. You remember I derived the Lagrangian. That was the lowest order. That was for a slightly different system. It was just one particle in a perturbed Minkowski spacetime. You can do something similar for a binary system. You can derive Lagrangians or Hamiltonians that are post-Newtonian expanded, so series in 1 over c. And at lowest order, you get the same term. I don't know if you can read. You get p squared. So this q is the separation of the binary. P is the linear momentum. So this is the same Newtonian Lagrangian that we obtained the other day. Then you have 1pn terms for the binary, which we derived, although in a different formalism the other day. We derived almost these terms, as a matter of fact. And then you can go to higher and higher order. Currently, this Hamiltonian is known to 4pn, and some results are known to 5pn, just as of last week. So this allows you to solve, and this Hamiltonian also includes the effects of the spins. So it's a very complicated calculation, but qualitatively, you can always map. The physics is qualitatively similar to that of a particle moving in a schwarzschild or Kerr black hole. And there is some deep reason for this, which is called the effective one-body model, but I'll not enter into that. But qualitatively, you can think of this, you can think that this Hamiltonian will give you an ISCO in the same way in which the Schwarzschild space-time will give you an ISCO. And therefore, at some point, circular orbits as defined by this Hamiltonian will become unstable, and the binary will plunge. So, yeah, this is what I've been showing a lot of formulae. Let's see if I can make this. Oh, I can't. Yeah, sorry, this is a PDF, so I can't show you. This was an animation of the in-spiral merger of two particles of two black holes. But unfortunately, I had to merge two different presentations, so in PDF it doesn't quite work. So sorry about this. So again, trying to show fewer formulae. This is the exercise that Andrea did, or that you did with Andrea, I think, the first day. So far we've been dealing with the in-spiral, the chirp part of the signal. So the in-spiral can be described by the post-Newtonian approximation. And at lowest order, as we derived the other day, what enters in the post-Newtonian approximation is the chirp mass. In fact, we wrote on the blackboard the other day an expression for f dot, the rate of change of the frequency, in terms of the chirp mass of the system. And this is some f dot, so you can invert that relation and get an expression for the chirp mass as function of these quantities, the frequency and f dot. And frequency and f dot are, in fact, something that you can measure. This is a power time, frequency. This is power in the frequency time plane for the first LIGO event. So this is, in a sense, a spectrogram. So you see here that there is an accumulation of power where the signal is. So you could use this, you could fit this banana shape and obtain f dot and f, and you can replace, and you can get a chirp mass of about 30 solar masses. I believe this is the exercise that you did, right? So this tells you already something about, it's not simply curiosity or astrophysics, but it tells you something about the nature of these objects. I don't know if Andrea mentioned that. So essentially, if you assume that these two black holes have roughly equal masses, you can convert this chirp mass into a total mass, and you get about 70 kilometers, 70 solar masses, which, if you convert that into a Schwarzschild radius, gives you 210 kilometers. So if these two objects were indeed black holes, you would expect that they should merge at about the ISCO separation for this gravitational radius. So I mentioned before that the ISCO for a Schwarzschild black hole lies at 6 gm over c squared. So for a binary system, the factor 6 could be different, and you need to get the exact value of that coefficient from the post-Newtonian Hamiltonian. But still, you would expect that if these two objects are black holes, they should plunge and merge when their separation becomes comparable to the radius of their event horizon. So at around a few hundred kilometers, in particular at about 200 kilometers, you should be able to see the merger. So if you convert 210 kilometers in fact, you can look at this figure and see where the merger takes place, because the merger corresponds to the maximum of the power. So it corresponds to about 75 hertz. So if you convert 75 hertz to a separation using Kepler's law, you get 350 kilometers. So it looks like the system merges when the distance between the black holes is about twice the sum of their event radii. So when the separation is about 4 gm over c squared. So this tells you that these objects must be very compact. If these were not black holes, but stars, they would touch way before they reach separations comparable to their gravitational radius. They would touch and start interacting tidally at separations way larger than this. So this shows you, just this picture and this calculation that you did, shows you that the objects that LIGO is seeing must either be black holes or they must be very compact. They could be, of course, in principle, be neutron stars. White dwarfs are probably not, well, they have a maximum mass and they're probably not compact enough. They could be neutron stars, but neutron stars cannot be this heavy. You can't have neutron stars of several tens of solar masses. There is a bound called causality limit that limits the mass of a neutron star to about 3 solar masses. So there is no way these can be neutron stars. They could be something else, something more exotic than black holes, but then the burden is on the proponents of those objects to argue that they shouldn't be black holes. All the evidence we have so far is that they are black holes. So you did this exercise, I think, for the first detection. I'm not sure for which one, for one particular example, but we have by now 10 or 11 black hole observations with LIGO Virgo, with masses that are typically around, well, they go from 10 solar masses, these are the individual masses, M1 and M2 for a range of events, from M1, for 10 solar masses up to the latest, the heaviest black hole measured has 50 solar masses. And there is also, of course, 170817, which is a neutron star merger, and the neutron stars have masses of 1.4, 1.3 solar masses, which is incidentally the typical mass of neutron stars when we observe them in the field and in binaries. And also you can try measuring the spins. In fact, I think I have a slide on the spins. Yeah, well, this is just a pictorial representation of the same of the LIGO detection, so LIGO Virgo detection, I should say. So the blue are the black holes. So the y-axis is the mass in solar units. The x-axis doesn't mean anything. The blue ones are the black holes that merge in the LIGO, during the LIGO observation runs, and the size is proportional to the mass of the black hole. So you have all these big black holes. What they represented here are also X-ray binaries, so black holes that are observed in the X-rays because they interact with a star. So these are systems that are comprised of a black hole plus, maybe you should switch off the light. Oh, maybe it's better. These are systems that are comprised of one black hole and the main sequence star. So the main sequence star is tidally disrupted. The black hole accretes the mass of the companion and then shines in X-ray because of the efficiency, radiative efficiency that I mentioned before. And using the spectrum of the disk and the dynamics of the system, you can measure the masses. And these black holes that happen to live in X-ray binaries tend to have smaller masses than the LIGO ones. Why that is the case, I don't think it's obvious. It was quite unexpected. So people most people, I should say, expected black holes for LIGO that were of 10 solar masses, maybe 20. Nobody expected these very large black holes of 50 solar masses or more. Then you have a gap here, and at low masses you have the neutron star events. So these are these two, the orange ones are the LIGO, is the LIGO detected one, and the yellow one are other known neutron stars measured electromagnetically. And as you can see, the most massive one has 2 solar masses. In fact, the highest measured mass for a neutron star is actually 2 solar masses. And I was saying there is also a causality limit here. So it's not surprising that there is this gap. This was sort of expected. I don't know how many people are interested in the astrophysics. Well, I'll say a few. Let me see. Yeah, well, I'll say just a few things very quickly. So one of the things you can do with LIGO is, of course, trying to understand, or LIGO and Virgo, is to understand the origin of these black holes. Why do they have such a large mass, for instance? Well, it's a very tough problem because it has to do with stellar evolution. So we believe that the black holes in the stellar mass range, so those that we should be concerned with when we use LIGO, are produced by supernova explosions, essentially. Type 2 supernova explosions. And actually, a supernova could explode and give rise to a neutron star. In fact, we have an example, the Crab Nebula, in which we know that a neutron star was formed. And whether a supernova ends its life as a black hole or a neutron star depends very much on the mass, initial mass of the star, the metallicity of the star. Metallicity in astrophysics means anything heavier than helium. And so according to the initial mass of the star, you can get a neutron star in certain regions of the space, you can get a black hole, so you can get an explosion, then matter could fall back onto the core and make the core collapse, so you form a black hole by fallback, as people say. Or you could have direct collapse to a black hole, or you could just have an explosion. If the initial mass of the star is between 140 and 260 solar masses, you have what is called a peri-instability supernova, which explodes without giving rise to any compact object remnant, if the metallicity is very small. So it's at least a two-dimensional problem, so you need to solve the equation for the stellar structure at least in a two-dimensional space, but it's even more complicated than that, because you also need to include the effect of rotation, which is not something which is only now being started to be understood, and also you need to do this in a binary system. This plot here is for which dates back to more than 15 years ago, is for isolated stars. You need to do this in a binary. There are no hydrodynamical simulations of stellar evolution for binary systems. So it's a very tough problem, and this is why I think it's fair to say that we don't understand this problem well. So for instance, one of the things that we could or that people working on this could conclude from the fact that the LIGO black holes were very heavy is that stellar winds that act during supernova explosions were much weaker than expected. So stellar winds, it means radiation pressure. So if stellar winds are like the solar wind, it's the same thing as the solar wind. If stellar winds are very strong, they tend to strip gas from the system when the supernova explodes, and therefore you get a small black hole mass. This is the mass of the black hole as function of metallicity. If the winds are weak, you get a larger mass. There is also dependence on metallicity again, because the metallicity affects the cross-section of the gas with the photons. So if you have a heavy nuclei, they have a larger cross-section with the photons, so it's easier for winds to strip mass from the star. So the smaller the metallicity, the lower the cross-section of the gas with the photons is, and the larger the final mass of the black hole is. I don't want to enter into the detail of this plot because I'm not doing well with time. So this is the idea. So LIGO black holes were bigger than expected, so it means two things: that these black holes were probably formed in very low metallicity environments, one thing, and the second thing is that winds are probably weak. And this is something we understood. So some people had predicted that, but most of the community thought that the maximum black hole mass would be something like 20 solar masses. So this came as a sort of a surprise. I don't want to show this, or maybe, yeah, so I mentioned before, maybe I can show it in the previous slide. So there was this pair instability gap here. So I mentioned supernovae with these masses, the masses in this blank here, do not give rise to black holes. And in particular, this causes, it's not obvious what is the maximum mass of a black hole. So let me see if I have it here. Yeah. So I want to say a couple of words about this pair instability gap. So normally, type 2 supernovae, they start burning their hydrogen, then I don't know if you've ever seen this, but probably some of you have seen this. So you start producing heavier and heavier elements until you reach iron. Iron is the most stable atomic element, the one with the lowest binding energy. So this is the most stable configuration. When you when you exhaust all the iron that you can burn, you can't produce heavier elements because it would require injection of energy from the outside, and therefore you explode. And this is what gives rise to a supernova. For stars that are very massive, so in this 130 to 160 solar masses range, and very low metallicity, at some point the conditions are such that you can't reach the formation, you can't form an iron core. So essentially what happens is that photons start interacting with the atomic nuclei and produce pairs of electrons and positrons. And this, so photons are transformed in pairs, and this decreases the radiation pressure of the star. So photons are what keeps these stars together when they start transforming themselves into, electron-positron pairs. The pressure of the star drops, and you have this pair instability supernova explosion. So, this is the physics behind this pair instability gap. And in particular, however, when you're right below, if your star initially has a mass which is slightly lower than 130 solar masses, you can still produce, you get what is called a pulsational pair instability supernova, which can produce a black hole. And in fact, it has been argued in the literature that this pair instability, these pulsational pair instability supernovae are the reason why we see an excess of black holes at about 35, 40 solar masses. So the fact that most LIGO objects have masses which are on this order of magnitude might be due to this pair instability, or actually to stars that are about to get pair instability unstable, but somehow manage to produce a black hole. And this is very exciting because this is, as I mentioned, it now seems that we might even have black holes with masses as high as 50 solar masses. And these are marginally marginally inside this instability gap. So this 50 solar mass black hole is one of the last detections, is one that is posing trouble. So if you look at this plot here, there should be nothing at 50 solar masses. most of the maximum mass that you could get would be about 35, 40 solar masses, so there should be nothing at 50. Of course, a factor, a 10% difference is not much for astrophysics, so it could be that this peak is slightly to the right, but if we keep seeing black holes that are much more massive than 50 solar masses, this would tell us, would mean that we got something wrong about the physics of the pair instability supernova. Let me see. I think I'll stop here for this part, for the astrophysics, because I want to say something about. Is there anyone who's particularly interested in the astrophysics? Yeah. 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 Like what? Like, I mean, there are two other processes that could. So they could be from population 3 stars. So population 3 stars are stars formed when the universe has very low metallicity at a redshift 1520, and because the universe has low metallicity is a proxy for time in cosmology. So if these stars form early, they formed in very low metallicity environment. Therefore, they are very massive, and they give rise to black holes, which are also very massive. They could be as massive, they could even be above the pair instability gap. The question is, and I didn't want to discuss about that plot, is that typically when you form a binary, it merges very fast. So it's very difficult for for population 3 remnants, black holes forming from population 3 stars, to survive until redshift 0.1, which is where because that's you would need to delay their merger, their evolution by several gigayears. So in fact, if you go back in time, this is a plot that shows the merger rate density as function redshift for different metallicities. So if you have very low metallicity, 0.1, you get a peak on the formation of black holes at about redshift 4, and if you go to even lower metallicity, you can go to much higher redshift. But then most of these events, this is a merger rate, so most of these events merge immediately, and very few survive until today. The other possibility is that some people have entertained is that these black holes are primordial. There was a lot of excitement after the first LIGO detection, because people thought, well, maybe these black holes are the dark matter. So these would be black holes that formed well before I think, and even in the radiation year, I'm not sure, but well before the CMB. And they could be the dark matter. The problem is that because they formed before the CMB, they would accrete. In general, black holes accrete, as I was mentioning before. So when they accrete, they produce photons, they produce X-rays. And these X-rays would cause spectral distortions in the CMB. So you would be able to, if these primordial black holes that we see in LIGO were all of the dark matter, we would be seeing them as spectral distortions in the CMB, which is not something that we see today. And then there are other problems with the primordial black holes proposal. So yeah, so either you form black holes from stellar evolution, or they're primordial. There is not any other possibility. I don't know if this is. Oh, okay. I see what you mean. A second generation. Yeah, that is unlikely, because when you run the numbers, I mean, it's unlikely. So because yeah, so say 1%. Let's put it this way. Say 1% of the black holes that exist as isolated objects. What is the probability that two black holes that come from a merger meet each other? So suppose suppose that only 1% of a population is given by I don't know, black people in a white background. What is the chance that two black people simply randomly, without knowing each other, so it's 1% squared, so it's 10 to the minus 4. I don't know if that makes sense. So people have studied this, and it turns out to be a small probability. What do I want to say? I don't want to enter into the details. So I mentioned there is evidence that we can measure black hole spins with LIGO, or Virgo. I keep saying LIGO, but it's a LIGO scientific collaboration, so it's Virgo and LIGO. So there are in fact two events for which we have marginal evidence for the spins. It's very difficult to measure spins with ground-based detectors because spins are a post-Newtonian effect that is important during the inspiral. So the detector is such that we don't have much signal-to-noise ratio in that region of the evolution. But there are still two events for which we have marginal evidence for the spin. These are the posterior distributions. Again, these are the same posterior distributions that we talked about this morning, which are produced again from a Markov chain Monte Carlo, comparing to the data. And this is the spin range. This is spin of object 1, spin of object 2, ranging from -1 to 1. And in fact, and you also have the orientation of the spin. So in one event, the spin of the primary black hole, so the more massive black hole, turns out to be if you want the maximum likelihood estimator, turns out to be of about 0.5. And you also see a misalignment. So the spin is not aligned with the orbital angular momentum. This is not a particularly significant measurement, but there are hints that you could have moderate misaligned spins. And in particular, in that event of 50 solar masses, which I mentioned before, which is the one giving us trouble for the astrophysics, you also have some evidence for large spins for both objects, and perhaps even aligned spins. So this, when you put this together with astrophysical models, essentially, I think it's fair to say that no astrophysical models can produce at the same time the mass function for the black holes observed by LIGO and reproduce these results. So there's a lot of food thought for astrophysics here. And in fact, this is what I was saying, but I'll skip it. So in the last 23 minutes, I want to say something about this part of the signal, the ring down part, because I spent all these 5 lectures talking about the inspiral, the binary system, the quadruple formula, and so on and so forth. And I want to say a couple of words about how we describe the waveforms in this ring down phase. Ring down phase in which you have you have the merger first, and then you end up with a black hole which is perturbed and which sheds away these perturbations on in gravitational waves. So to give you, we talked about linear theory the first day. So what you could do to study suppose you have a Schwarzschild black hole or a Kerr black hole, and you want to perturb it. So the procedure will be the same as the one we discussed in the beginning of this lecture. So you take the metric and you add a perturbation h mu nu, which is small. And then you get your field equations at linear order, which we even wrote at some point. I wrote the equations for a generic metric perturbation over a curved vacuum space-time, and that turned out to be box h mu nu. Then you had a coupling between Riemann and h mu nu equals 0. So and then you could study that wave equation. So now I want to do something easier because I don't have the time to go through all the details. Instead of perturbing a Schwarzschild or Kerr black hole, I want just to take a Schwarzschild or Kerr black hole and study the dynamics of a test scalar field on top of it. So if I have a scalar field on a Schwarzschild black hole, let's do it in the no-spinning case because it's easier. The scalar field satisfies the Klein-Gordon equation. So G mu nu is here the metric of the black hole, the background, Schwarzschild black hole indeed. And then you have, this is the curved box operator equals 0. And this is a relatively easy equation because instead of having a tensor field, h mu nu, I have a scalar field. So for a scalar field, you know from for instance, from quantum mechanics, that it's convenient, especially if you're in spherical symmetry, it's convenient to decompose the scalar field into spherical harmonics. And also, it's convenient to decompose the scalar field, the time dependence of the scalar field, in a Fourier series. So in practice, what you do is to assume an ansatz of this kind for the scalar field. So scalar field will be given by some spherical harmonics, a sum over spherical harmonics, L and M, multiplied by a Fourier phase. Then you will have an integral over the omega, if you want to include several frequencies. And then let me make this assumption, which at this stage is just an ansatz, so I don't know if it will work. I'll assume that the functions, the coefficients that multiply the spherical harmonics are just function of radius alone. So you can come up with an ansatz like this, or it can be given to you, but once you have this ansatz, you can insert it into the Klein-Gordon equation. So what happens at this stage is, well, it's sort of a miracle, but it's not, the equations separate because of the symmetries of the problem. So what happens is that you end up with one equation alone. From this Klein-Gordon equation, you end up with one single ordinary differential equation. So all the dependence on time, the dependence on the angles factors out, and you end up with just one equation for the radial variable. So this r is again a function of small r alone, and this v is this simple function of radius, mass, and azimuthal, not azimuthal, quantum number L. And this p, I use a different symbol for p, because you get a similar equation if you consider a vector field, if you consider a tensor field on a Schwarzschild background. And the equations that you obtain are very similar to this one, and the only thing that changes is this small p. So this small p depends on the helicity of the perturbation. So r star here is the tortoise coordinate. So those of you who have seen the Schwarzschild metric and geodesics will remember that the tortoise coordinate is this is very convenient to study the causal structure of Schwarzschild spacetimes. And it ranges from -infinity at the event horizon to +infinity. So, so this derivative is with respect to radius. So what do you have here? You have an equation which looks like the Schrödinger equation. So you've all taken quantum mechanics at some point in your studies, and you remember when you look for the eigenvalues of the Schrödinger equation, you get an equation of this kind, where this omega is actually the energy in quantum mechanics. So you have an equation which looks like the Schrödinger equation. And as I was saying, you can do things not only for Schwarzschild, but also for rotating black holes, curved black holes. And also, you can do that, you can do a similar decomposition for vector fields or even for tensor fields, so for the metric perturbation. It's a bit more complicated for tensor fields, especially when you have black hole spins. So your decomposition will not be anymore in terms of spherical harmonics, but in terms of what we call spin-weighted spheroidal harmonics, but it's just a technical problem. So in the end of the day, you can have a spectral decomposition of your perturbations, be them scalar, vector, or tensor, in terms of a radial function, a radial eigenfunction, I should say, that satisfies a second-order ordinary differential equation. So there is no more dependence on the angle here. And this, again, looks like the Schrödinger equation. So when you do the quantum mechanics 101, one of the things that the exercises that you're typically asked to do is to solve the potential barrier equation. So you have a Schrödinger equation with a rectangular potential barrier, And you're typically told that the system is isolated, so you're told to impose outgoing boundary conditions at the two ends of this of your one-dimensional problem. So here the situation is similar. So we have a Schrödinger-like equation, which is in terms of a radial variable. And if you plot the potential, this potential V that appears in the equation, it has a peak outside the event horizon of the black hole. So R equals infinity, of course, means spatial infinity. So the system is isolated, so you should impose that your perturbations, you should impose that nothing enters the system. So you impose outgoing boundary conditions here. At some place here, you will have the event horizon, so nothing can escape the event horizon of a black hole, so you need to impose ingoing boundary conditions. So, and this is exactly the same as what you do for the rectangular barrier in quantum mechanics. And as in quantum mechanics, when you have a boundary value problem and impose boundary conditions in this way, you select, maybe I should go back to this equation, if you impose outgoing boundary conditions and infinity and ingoing boundary conditions for this equation, just like in the case of the Schrödinger equation, you get a quantized spectrum, a discrete spectrum for your energies. Here you get a discrete spectrum for your frequencies. So it's exactly the same as the Schrödinger equation. The difference here is that because this potential, well, in general, this potential will be complex. Well, you don't really see it from here. Well, what you find is a discrete spectrum of complex frequencies. So these frequencies turn out not to be real, as in the case of the Schrödinger equation, but they're complex. And these are what we call the quasi-normal mode frequencies. So what does it mean that they are complex? So if you look at these ansatz here, so you have the exponential of minus I omega t. It would probably help to write, but you can write it in your notes. If I decompose omega into a real part and the imaginary part, the real part will give me a sine or a cosine, and the imaginary part, because there is an extra I here, will give me either a damped exponential or an exponential or a divergence. So according to the sign of the imaginary part, these perturbations may blow up or decay exponentially. So one of the things that you get from this exercise in particular is that the imaginary part is always such that this exponential here is exponentially damped. So this means that Schwarzschild and Kerr black holes are linearly stable. So this is why we get that quasi-normal mode part that I showed here. You see this exponentially damped signal is due to that, to these quasi-normal modes. And these oscillations are due to the real part of the quasi-normal mode frequencies. Yes, so I want to. So what is interesting, this is one of the last things that I will be saying, is that so you end up, by solving this boundary value problem, you end up with quasi-normal modes frequencies that are functions of the mass and the spin of the black hole, and you have these decay times for the quasi-normal modes that are also functions of the masses and spins. And in general relativity, they are, I mean, you can try, so you have several quasi-normal modes because they are parameterized by L and M, but they are all functions of the same two quantities, M and J, M being the mass and J the spin of the black hole. And this is called in general relativity the no-hair theorem. So all the physics of the ring down is parameterized by just two numbers, the mass and spin. So you could try to, so if you measure the mass and spin, for instance, from the final black hole, from the in-spiral part of the waveforms, you could try to test consistency with general relativity. Or said otherwise, for instance, you measure the mass of the spin from L equals to M equals 2, from the least damped quasi-normal mode, as we call it. Then you could try to see whether the higher order modes are consistent with this prediction. So in a sense, you can do a null test of general relativity using these quasi-normal modes. There were more things I wanted to say, but I think this is getting late, so let me... is it clear? Are there any questions on this? The last 5 minutes, I wanted to make the connection to the null geodesics in Schwarzschild and Kerr, but I think I'll skip this. So the last 5 minutes, I'd like to talk about, so I talked a lot about LIGO. I wanted to go to my favorite topic, which is LISA. So let me see what I have. So I forgot what I have actually. Yeah, so I want to say that LIGO are not the biggest, LIGOs are not the biggest black holes that we expect there should be in the universe. As I mentioned, LIGO black holes are formed by stellar evolution, essentially, as the remnants of supernova explosions. Or they might be primordial, although that proposal has many problems, as I was saying. There are other black holes that we know exist in the universe, and these are supermassive black holes. So for instance, we have one in the center of our galaxy. So again, I don't have the animation because this is a PDF, but you can track the motion of main sequence stars around Sagittarius star, which is a point like a radio source at the center of our galaxy. And you can observe them for for 25 years now. And if I were able to run the animation, you would see nice elliptic orbits around the center of the galaxy. And by measuring the period, you would be able to infer the mass of this dark spot in the center of our galaxy. And it turns out to have 4.5 million solar masses. These are called supermassive black holes, or massive at the very least. So the idea is that, in fact, we see these black holes pretty much in the center of all galaxies in which we look, and in fact, you can even correlate the properties of these black holes, and in particular their mass, with the properties of the galaxy. So even though these black holes are tiny for galactic standards, you can so they are subparsec. You can correlate the mass of these black holes with something which is called the velocity dispersion of the galaxy, which is a proxy for the properties of the galaxies at kiloparsec scale. So this is what in astrophysics we consider a tight correlation. It's a power law. So we believe that in each galaxy there is one such massive black hole with mass depending on the properties of the galaxy. And from the lambda CDM model and from observations themselves, we believe that galaxies merge all the time. So in the lambda CDM model, you start with small halos at very high redshift, and then these halos merge until they form the big galaxies elliptical galaxies we see today. So whenever two galaxies merge, we believe that the contained black holes also merge. And this could give rise to a gravitational wave signal, just like the LIGO mergers. I'll skip this slide. So how do you see the gravitational wave signal from these black holes? Well, as I mentioned this morning, you can't do this on Earth. There is a barrier at frequencies of about a few hertz on the ground, which is due to seismic noise that prevents you from going to lower frequencies. So I talked about LISA this morning, a third generation detector. This is the sensitivity of LIGO today, or if you advanced LIGO 1, yeah, this is LIGO. Advanced LIGO 1 is the LIGO as it was in 2015. Advanced LIGO design sensitivity is this one, and then you can improve things. You can go down to this curve, which corresponds to this cryogenic third generation detectors that I mentioned today. So you can improve by the sensitivity by, I think it's 1 or 2 orders of magnitude, which corresponds to, if you think about it, an increase in volume of 5 orders of magnitude. So if you increase the sensitivity of the strain you can detect by a factor 10, the volume that you can see in the universe increases by a factor 1,000. So this would be a huge improvement. So for instance, this Event Horizon, Einstein Telescope or Cosmic Explorer detectors will be able to see all the neutron star mergers in the universe. Another possible detector that we'll have is LISA at millihertz frequencies, and we also have these experiments that I mentioned in passing before, which are called pulsar timing arrays, which are ongoing experiments. And these all allow going below frequencies of a few hertz, which is where you're limited by the seismic noise. So I want just to conclude, I want to say a few words about pulsar timing arrays and LISA. So pulsar timing arrays are experiments that, again, are ongoing. There are 3 experiments in the US, in Europe, and 1 in Australia. So what we do is to track to time pulsars. Pulsars are rotating magnetized neutron stars whose magnetic field is misaligned with the rotation axis. So they're essentially lighthouses. So whenever the magnetic dipole points at you, you receive a radio signal. And being these typically very old objects, in particular we track millisecond pulsars, they are very stable clocks. So they're more stable than atomic clocks. So you see we see about by now maybe 30 of them, all in the galaxy, they're close to us, they're in our galaxy. And they're essentially as clocks in the sky. So remember we did this calculation yesterday about the change in frequency of a laser going back and forth between 2 mirrors. The situation is the same here. You have the pulsar provides you with a radio wave whose frequency changes if a gravitational wave passes by. This is exactly the same calculation that we did yesterday. So if you want, you can think, so a passing gravitational wave will perturb the time of arrival of the pulsar. So in a sense, this would be like LIGO in the sky if we knew the distance to the pulsar. Because we don't know the distance to the pulsar, we have to use several of them and do cross correlations, etc., etc. But we can look for what we call stochastic backgrounds, unresolved stochastic backgrounds of gravitational waves in the nanohertz band. So these are, if you want, this is like LIGO in the sky with a very long arm given by the distance to the pulsar, and it turns out to be sensitive to gravitational waves at frequencies of nanohertz, and we can put very strong bounds on the existence of such a stochastic background of gravitational waves. And in fact, it's in a region where we would expect to have seen a signal already based on our understanding of the astrophysics based on this plot. So if we take this together, galaxy formation plus lambda CDM plus presence of black holes in the center of galaxies, you would expect a stochastic background of gravitational waves at nanohertz frequencies that we haven't seen yet. So these are these Gaussians here, these curves here are the probability distribution functions for the amplitude of the signal or the log of the amplitude of the signal that would be visible by pulsar timing array according to different astrophysical models. These are also other astrophysical models. And the region that's excluded by current observations is this shaded area here. So we're in the region in which we would be able to, we're starting to exclude astrophysical models. So we could have a detection anytime, and we'll certainly have a detection. So some models are widely excluded, for instance, such as this one. And with the SKA, and in general with better radio telescopes, we'll see certainly a signal, I believe, in the next 10 years. The other experiment I mentioned is LISA. So I talked about this already. This is a cartoon of LISA. The one thing I didn't say today, and this is one of the last things I will be saying, is that LISA will be able to measure massive black holes with masses between 10 to the 4 and say 10 to the 7, up to redshifts of about 20. We don't even know if black hole binaries exist at these high redshifts. And this is the signal-to-noise ratio that I defined this morning. LIGO, for a comparison, has signal-to-noise ratio of a few tens. With LISA, we reach signal-to-noise ratios of several thousands. So this is a much more sensitive detector than LIGO. And in particular, LISA will also be able to see the same. So you can see there is a region here where the LISA sensitivity extends to tens or maybe 100 solar masses. So these are the same black holes as in LIGO. So in particular, if we had had LISA at the time of the first LIGO detection, we would have seen the same signal in LISA as well, or better. And I think I have it. So this is LIGO, what it will be like in the 2030s, roughly. And this is the range, mass, luminous distance range of LIGO as function of the signal-to-noise ratio, and this is LISA. So you see there is an overlap. So what we will be able to do with LISA will be to observe the LIGO binaries at low frequencies when they're far apart, years or months at least before they enter into the LIGO band. So you'll be able to it's not going to be an easy observation because LISA, this is in the region where LISA is less sensitive, but still we should be able to see at least the most massive LIGO binaries years or months before they emerge in LIGO. We should be able to predict when they emerge in LIGO to within 10 seconds, roughly. So we should be able years before to tell them on March 15th, 2019 at 4 o'clock you will see plus minus 10 seconds, you will see a merger. So the binaries, we see them in the LISA band. They will go out of band for weeks or days according to the parameters, and then they will reappear in the LIGO band. And this opens a whole lot of possibilities for testing astrophysics and fundamental physics. Just the last 2 slides, and then because then I have to go catch my flight. So I talked a lot about LISA. So I wanted to avoid giving the impression that LISA is very far in the future, especially because you guys are very young. So LISA is a mission approved by ESA almost 2 years ago now. It's in what we call now phase A, which means that we're finalizing the mission design, after which essentially 2 companies will be asked to give quotes in a certain sense for producing the detector. And then there will be, so at the end of phase A, we will actually start, or in a few years' time, in a couple of years' time, we'll start building the detector, or they will start building the detector. And this industrial production phase will take about 10 years, so LISA should be able technically to fly by the end of the next decade, 2030s. And there are political reasons why ESA would like to fly it before its nominal launch date. So there is a nominal launch date, which is 2034, but they would like to fly it somewhere between 2030 and 2034. And technically, we should be ready to fly by the end of the next decade. So it's a very, especially if you're a PhD student now, this is a very a timeline which you should keep in mind. And just to give you the very last, I promise, slide, just to give you, to try to advertise LISA as on the one hand as a wonderful mission, but also as a very nice or very difficult problem. I mentioned before we mentioned this morning the likelihood. So, and I mentioned that if you want to estimate the parameters of a gravitational wave source, you need to find the maximum of that likelihood. And I mentioned that if you have just one gravitational wave source, you have 15 parameters describing the source. For a binary, you have the 2 masses, you have the spins, which are vectors, therefore they have 6 components in total, so that's already 8. Then you have the initial frequency of the binary, you have the merger time, you have the sky position, which are 2 angles, you have the orientation of the binary with respect to us, etc. So if you count, there are 15 parameters. So when they find the maximum of the likelihood for LIGO binaries, it's a maximization problem in 15 dimensions, and this is why they use MCMCs. For LISA, the problem is even more complicated because most LISA sources will be long-lived. They will be on all the time. Unlike LIGO, in which you have a source, then silence, then another signal, then silence, in LISA, all sources will be on at the same time. So I don't expect you to be able to, well, or maybe we can, I mean, there will be, so for instance, I mentioned already this morning that in LISA there will be hundreds of thousands of white dwarf binaries in the galaxies, which are in band, so many that some of them will degrade the sensitivity of the instrument, and at least 10,000 of them should be resolvable. There will be at least 10,000 sources that you need to extract from the data just from the galaxy alone. On top of this, there will be supermassive black hole binaries, which is what I mentioned, which could range from a few to 100. We'll have also other sources called extreme mass ratio spirals, of which I have no time to talk. But you have all these sources on at the same time. So if you want, it's a maximization problem in 15 times tens of thousands of dimensions. So you'll have a function, the likelihood, defined in a parameter space of tens of thousands of dimensions, and the task is numerically finding the maximum, the global maximum of this function. So, and this is what we call the enchilada problem. So enchilada is a Mexican dish when you put everything together. And we want to disentangle, we want to recreate the ingredients out of the enchilada. So we don't have the LISA data yet, but if you're interested in this, and in general in Bayesian data analysis, we're running a mock data challenge now, where we produced simulated data based on our understanding of astrophysics, and we're handing those data out to people who want to try with MCMCs or maybe with machine learning, with techniques to try to solve this maximization problem. And I think, so if you want to sign up for a mission, this is the consortium. This is, especially if you're young, this could be a nice, nice career move. I think I'll stop here because I think it's time to go.